we've got n, which is 3 times 10 to the 20 atoms in 3 accessible states. I'm going to give the energies of these states as 0, epsilon, and 4 epsilon. I'm not going to tell you what epsilon is in terms of joules because it doesn't matter. We're going to think of epsilon as like a characteristic energy for the system. All right, often that's what happens. Rather than relating everything to this SI joule unit that was randomly, defined in terms of certain things that happened on this planet 200 years ago, all right, rather than relating it to that, irrelevant unit, we're going to relate to a unit of our system. All right, so if I've got a system with several different energy levels, I can say, hey, look at energy level 3. That's going to be my characteristic energy level. All right, and then what's energy level 4? Well, it's 3 times my characteristic. What's energy level 1? Well, it's 1/5. Oh, so it's a much more natural way to look at the system. All right, so I'm not going to tell you what epsilon is in terms of joules because it doesn't matter. Now, if I want to compare this to something else that's going on, or if I wanted, the value of K Boltzmann, that is given in terms of the standard SI units. So that's when I would need to determine what my characteristic energy scale was in SI units. But if I'm just interested in this system taking place in isolation, then I don't need any of that business. All right? So we've got these atoms in 3 accessible states, and we have a total energy (1/2) capital N epsilon. So I've got 2 constraints. I only have 3 unknowns. So that means I only have to tell you one of the unknowns, and you can determine the other 2. All right, so I could tell you how many atoms are in state 3, and then you could use the fact that the total energy is 1/2 capital N epsilon, and that the total number of atoms is capital N to determine the number of atoms in state 1 and state 2. It's helpful that the energy associated with state 1 is 0. That means that state 1 doesn't contribute to the computation of the total energy. Well, you may think that that's contrived, and you might have some of a point there. At the same time, if I had a system with 3 energy states, all I have to do to make it similar to this one is just take all the energies and subtract the energy of the lowest state. All right, now I'd have to do that here as well. All right, I'd have to give the energy in this new scale where I subtracted the energy of the lowest state everywhere. But once that's done, it's done. All right, and now I don't have to worry about the occupation of the lowest state in as far as looking at the total energy. So that makes it convenient. All right, now what I'm going to do is ask you to calculate the entropy, for various occupation numbers. So let's see what the entropy is here. K Boltzmann log of capital N factorial minus log of N1 factorial, N2 factorial, and 3 factorial. Now, we'll be working with numbers that are large enough to justify unapologetic use of Stirling. So I'll have Now, there are some cancellations that take place. One of them is fairly obvious. Remember that capital N is equal to N1 plus N2 plus N3. All right? That one's fairly obvious. To get the other one that's sort of nice, I need to separate out the log of N1. So I'm going to write log of N1 as that. All right? And if I do that, here and here and here, and I distribute, we'll find that capital N log N cancels. So at the end of the day, our expression for the entropy is given like this. All right? Now, we know K. Boltzmann. We're just going to use K. Boltzmann. Is about 1.38 times 10 to the minus 23rd joules per Kelvin. You could use more digits. As we learned earlier, I had forgotten, things have been redefined, the Kelvin in particular, to give us an exact value of K. Boltzmann in SI units. All right, so you can use more digits if you want to, but this is going to allow us to determine the entropy as a numerical value in joules per Kelvin. All right? Some of the problems may cause you to think that you need to keep 15 or 18 digits. You do not need to keep 15 or 18 digits. Your answers should not be given to more than at most 4 digits. Okay? All right, but at any rate, we can actually use this to calculate the entropy for various configurations.